Okay, I think we can get started now. Right about now because it's actual time to get started. Once again, my name is Daniel Afedra, and I'm a talent manager at Tonga. And I've been working with Tonga since 2019 as a software developer and now as a member of staff. So it's good to have you all here. With me today is my colleague Oghomwen from Nigeria, and I am from Uganda. So Oghomwen, maybe you can say your greetings to our to the people that have joined the bootcamp today.
Hi everyone, happy to be here today. Hope we're all excited to get into these topics. Really interesting lineup. Yeah, looking forward to speaking with you guys in a few minutes.
Thank you, IG. I will be giving you the agenda for this bootcamp, and it's pretty interesting because this bootcamp is going to be available for 1 week. And during this session, we're going to be training you on a topic of data structures and algorithms, which is a very important concept in the field of software programming or development. Many times we watch YouTube videos and tutorials or read some books to teach us how to code, but then few books or few people really reach out to learn the data structures and algorithms, or in general, the computer science concepts. And so we're here to bring that to you. This is the first bootcamp, and then we are going to have many more bootcamps concerning other computer science concepts. So please keep tuned to our Tonga channels. You can follow us on the different social media handles: Facebook, Twitter, Instagram, LinkedIn. Feel free to follow us such that you can keep informed whenever these programs are being run. And then also you can always apply to join Tonga. We shall get to the nitty-gritties later on. And for now, let us get started with our agenda such that we can get into the interesting things. So for today, we are going to have an introduction, which I think I've already done a plethora of times, but because we've had different people joining at different times, I will still introduce myself and my colleague, Oghomwen, who's from Nigeria. So we'll also look at Tonga, because I believe we have some people here who are already Tonga developers, but I know we have some new people who are hearing about Tonga for the first time, or what about Tonga through the advert. So I'll be talking about Tonga as well. And then also the setup for this bootcamp throughout the 5 days, Monday being the first, and then the last session being Friday. Well, today and tomorrow we shall be looking at data structures. And then for Thursday and Wednesday, we are looking at algorithms, and then we'll wrap it up on Friday. Yeah, so for today, particularly, we're looking at data structures, and then we'll end this with closing remarks. Still, for each session, we'll have closing remarks. However, we shall also have closing remarks concerning concepts now on Friday. So that is the agenda for today. And once again, my name is Daniel Afedra, and I'm a talent manager at Tonga. So I'll be taking you through this bootcamp, and with me is my colleague Oghomwen from Nigeria. We really collaborate properly since we are from different parts of the continent, and I believe you also are from different parts of the continent. I've seen some people from Nigeria, others are from Kenya, and the different other countries. It's good to have you all from these different places, and it makes us happy that we have been able to reach out to all these places remotely. Yeah, so about Tonga, Tonga is a remote company, and our goal is to provide 21st century jobs for African youth. And most of these are tech jobs. So I know most of you could have been referred to Tonga by your colleagues who have experience working with Tonga. We have offices in Amsterdam, in Lagos, and also in Kampala, Uganda, where I currently am. Yeah, so that is a bit of it about the company. And if you want to read more about Tonga, you can simply check out our website. The link will be on the chat. But our mission mainly is to provide 21st century jobs for the African youth. And so, all right, so far, Tonga has, it was founded in 2015, and still we stand here in 2021. A lot has happened over the years, and then it will be very interesting for us to get to know how Tonga started and where Tonga is now. But in summary, Tonga has worked with developers and people from across Africa. Yeah, so had people working in Kenya, people working from Cameroon, Rwanda, Nigeria, Uganda, and many other African countries. We have 54 of them, so I'll not go through all of them. But I'm sure if you're here from your country, then Tonga has been there as well. So we have offices in Uganda, Nigeria, and Amsterdam, like I mentioned earlier. So basically, I'll also take you through what Tonga does. So Tonga matches the software developers and individuals, right, to teams and companies across Europe and also in the USA now. So you can work individually as a dedicated developer where you are hired as an individual to work for a company or one of our clients, or you could work in a dedicated team, still hired from Tonga. The team could vary. Some could come from Nigeria and Kenya. So it's a mix up of people that you work with, still from Tonga. And then this team is able to work for a company, one of our clients across Europe or USA. Yeah, basically that is what happens here at Tonga. So you simply have to, when you join in Tonga, you simply have to do tests, and then you're able to see and get access to a plethora of opportunities on the channel. I will be letting you know about this later on. Yeah, basically that is what we do at Tonga to match you to clients and opportunities that work for you. I already got a question in the chat about which language we're going to be using for this particular opportunity. And the answer is there's no specific language for data structures and algorithms. So it is always open to any general purpose language, as those you can see on your screen. And I'm very sure that you're familiar with this. And without losing a lot of time, I would like to dive into what we're here for, which is data structures and algorithms.
Daniel, there's a question rather in the Q&A section. Do you want to quickly answer that before we go on?
Yeah, so Barnabas is saying he's a developer from Zimbabwe and would like to know if Tonga is in his country already and he's willing to work for talent acquisition for Zimbabwe. Yeah, so Tonga is remote. I believe it's already in Zimbabwe. However, there is no Zimbabwe office at the moment. So potentially in the future, we shall be able to maybe open offices in Zimbabwe. I will still table that to the management. But for now, we do not operate in Zimbabwe as we do in other countries, Nigeria, Kenya, and Uganda. Yeah, and still this does not stop you from working for Tonga because we work fully remotely, and you can work from any part of the continent. I hope that answers your question, Barnabas. Okay, I think it does. So we move to the products here at Tonga. So for those of you that would want to grow your skills and expand on your skill set, Tonga provides to you an academy at no cost, which is filled with courses and tests. So after doing a course, it could be React, Node, or Ruby, and whatever. Like it's really a lot of courses on there that you can do if you want to expand on your skills. So feel free to visit the Tonga Academy. The links shall be shared in the chat shortly, and we'll be glad to have you taking on courses. And after finishing a course, we also have a testing platform where you can test yourself and your skills and how far you have come with a new technology or new skill you aim to acquire. And then when you feel that the skill is sufficient for you, then you can move to work on the platform where We have a works platform, which basically, like the name suggests, work, where we post all opportunities or jobs, as some people would call it, in the different languages, really. So you simply apply to the jobs that you are a good fit for, and then you get selected, and then you can start working immediately. Yeah, so that is basically a few of the products that we have to offer at the moment. So feel free to sign up for these, and then you can always access these beautiful products. The links will be shared shortly in the chat. And then for those that are not yet on Tonga, if you want to join Tonga, you have already seen that is a link to join Tonga. And it's a pretty straightforward process. But if you have any challenge, then you can reach out to any of us. We'll be glad to help you. And before we go into the data structures and algorithms, we are also hosting a global health hackathon, which will be running from March 19th to 20th of March. And applications are already open. So we shall still be sharing the links to this in the chat. But feel free to, if you want to participate in this hackathon and you want to, win amazing prizes and solve real world problems, and you also be able to meet the Tonga community, then this hackathon is for you. So besides the bootcamp, you can also use this hackathon to practice your data structures and algorithms. Yeah, thank you so much. And now we'll move on to the next slide, where we get into the data structures. So at this point, I would like to hand over to my colleague, Oghomwen, who's in Nigeria, and he's also a talent manager working with Tonga. IG, over to you.
Awesome. So before I go on, there's a couple of questions in the Q&A section. I'll just quickly try to answer them. Firstly, Nenji asks what certifications are required for developers. We typically do not require certifications for you to join Tonga, but I mean, it's always good to have certifications that show that you really do know what you claim to know as a developer. Certifications are not expressly required. And then Daniel also asked about the learning platform, if the courses are paid for, if they're free, or how expensive it is. The courses are free, and so you don't have to pay, really. Yeah, so before I go on, I would like to say that I'll keep an eye on the Q&A part of the room, and as well as the chat section. But if you have a question, feel free to put up your hand, and then I could allow you to talk and just ask by yourself, or you can also just type it in the Q&A section. Yeah, so let's get right into it. Data structures, why are they important to talk about? All right, so the context I really want to set for this is, firstly, that data structures are the building blocks for really sophisticated applications. You really cannot develop applications that are built well and really sophisticated if you don't have the right knowledge of data structures. Secondly, it's extremely important because choosing the right data structure for each task is really critical. You can choose the wrong tool for the right job if you do not understand data structures. And so if you do choose the right data structures for the kind of tasks that you want to solve or problems that you want to solve, you'll find that you already are halfway done solving your problem. Which takes me to the next point, which is that an ill-suited data structure could also result in slow run times or unresponsive code. So you could choose a data structure and think you're going to go ahead and solve your problem with that, and find that even if you do have a solution, it could run really slowly, and so you don't have any benefit from that, or your code might not even be responsive in the end. All right. So the setup for this is that today we're talking a lot about the theoretical aspects of data structures, and then tomorrow we'll do a lot of practice, and then also Q&A and a live feedback session. So I'll give an introduction. Firstly, I would also want to say that the concept of a boot camp typically that we're used to are sessions that are short, that are intensive, that are and also rigorous. But this boot camp is not such in that sense, because as much as it is short, it's not going to be extremely intensive, and it's not so rigorous, because we are using it as a starting or as a conversation starter for people who are really getting into this kind of things, right? So think of it as the boots in terms of booting a computer, for example. So this is to get you started, to boot you up into getting into more advanced conversations around data structures and algorithms. And because we are all at different levels in our careers, some of us are beginners, some of us are mid-level, and some of us are maybe really experienced, we might find that certain areas might be very easy for us or very difficult depending on where we are at in our career. But I've tried to structure this whole presentation in such a way that wherever you are in your career, you would be able to ideally follow right from the beginning to the end. So if it all looks basic to you, please stick around. There's some advanced concepts that we do look at later on in the whole of the presentation. All right. Going on. The introduction for data structures is that a data structure is a specialized format for doing primarily four things: organizing data, processing data, retrieving data, and storing data. And there are a series of basic and advanced data structures. There are a whole lot of data structures. And I feel like a lot of us would have come across some of them that we'll mention in the course of this bootcamp. And they are all designed to arrange data to suit specific purposes. Data structures make it easy for users to access and work with the data that they need in very appropriate ways. And most importantly, data structures frame the organization of information so that machines and humans can better understand it. All right, moving on. In computer science and computer programming generally, a data structure is selected or designed to store data for the purpose of using it with an algorithm. In some cases, the algorithm's basic operations are very tightly coupled to the data structure's design. I'll explain this sometime in the nearest future. Each data structure contains information about the data, about the relationships between the data sets, and in some cases, the functions that can be applied to the data. For instance, for anyone who uses an object-oriented programming language, you would already know that the data structure and its associated methods are typically bound together as part of a class definition. But in non-object-oriented programming languages, there are functions that are defined separately to work with the data structure, but they're not technically part of the data structure. So that's the distinction between if you use an object-oriented programming language and if you use something else that's not. Okay, I think someone came late. Damilari is asking about Tonga and what Tonga really is about, most especially the course available online. I think maybe we'll answer that later. So I'll just leave it in the Q&A section. So I'll move on to the next. So we want to also just get some more information about why data structures are very important, right? We now know what data structures are. They allow us organize, process, retrieve, and store data, especially in applications that we write. And why are they so important? Firstly, typical data types such as integers and floating points that we are used to, integers being set of real numbers, and floating point values being sets of numbers that are entirely are not really real. So they have like decimal points. So something like 2.5 is a floating point value. And so these typical data types that many of us may be already used to are available in most programming languages and are generally insufficient to capture the logical intent for data processing and use. Applications ingest and manipulate and produce information, and they must understand how the data should be organized to simplify the processing. Data structures bring together the data elements in a logical way that facilitates the effective use, storage, persistence, and sharing of the data. And they provide a formal model that describes the way the data elements are organized. Now, I'll paint a scenario. Most of us have been to a mall. I don't know if everyone has. And when you typically want to buy stuff, you go to an aisle, and typically aisles are labeled with the items that are found in those aisles. And typically, items that are similar are put in a group together on an aisle or in a section in that aisle. Now, imagine if you walked into a mall that didn't have that kind of setup. Imagine if you walked into a mall where everything was everywhere. It will be extremely difficult to find what you were looking for. But because malls are typically organized in such a way that you can use a label to find something you're looking for easily, it then makes your experience a whole lot better, and it makes you able to process, buying whatever you need to buy as fast as you can be, right? And so that's why that's a real world example of why a data structure is extremely important. All right, let's just check the chat. Nothing new. All right, moving on. Again, continuing on why data structures are extremely important. Essentially, they are the building blocks for extremely sophisticated applications. They are designed by composing data elements into a logical unit representing an abstract data type that has relevance to the algorithm or application. An example of an abstract data type is customer name, that is composed of the character strings for first name, middle name, and last name. So there's a code sample on the right. I think even if you haven't written any code before, it should be self-explanatory. This is a Java sample code that is a class that has an abstract data type that represents a customer's name. You know that you cannot store something called customer name in one single string, uh, and then be able to use that in very sophisticated applications. Typically, you want to define a data type that can take in a whole lot more information and organize it in such a way that you can easily process it. So for example, with the class on the right, we see that there's first name and last name. So if I have an object of this class, customer name, what I could then do is take the object, and I can get out just the first name from the customer name. I can also get out just the last name from the customer name. Assuming it was a single string with the customer's full name that was comma separated or space separated, what I then have to do is do an operation on the string, split it up to get the different sections of the customer's name. But with this abstract data type, it is extremely easy to collect that data, to process it, to organize it, to store it. And so that's like the best example I can give at the moment for a data structure and its importance. I see someone raise their hands. She's going to look for you and allow you speak. Okay, okay. Tajudeen, do you still want to speak? I saw your hand. Hi, Tajudeen. Okay. So I'll just go on. There any new questions? Okay, no new questions. All right. So moving on. Again, it's not only important to use data structures, but it's also important to choose the proper data structure for each task. If you choose something that isn't a good fit for a task, it will result in really slow run times and also unresponsive code. All right, so let's also see what kinds of data structures we have in certain across any language. Really, you definitely find these types of data structures. Uh, the first one we'll look at is an array. An array stores a collection of items at adjoining memory locations. Items that are the same type are stored together so that the position of each element can be calculated or retrieved easily by an index. And this is like a representation of what an array is like. So picture a computer memory in your mind and assume it has slots, square slots, like the image you see on your screen. And each slot has an address. Let's say 1, 2, 3, 4 for 4 slots within the computer memory. The first slot being represented by the address number 1. But typically in programming or computer science, we start numbering at 0. But for this situation, let's just say we're starting at the number 1, right? So an array is a data structure that stores data in adjoining memory locations, which means that it takes a series of location or locations in memory and stores data across those locations. And so what you find typically with arrays is that they have fixed sizes. They are typically fixed in length because you cannot have an infinite amount of space, adjoining amount of space available for you in memory. And so if you typically assign or declare an array with a certain number, it's not possible to really extend or change the size of that array without destroying it and creating another one. Yeah, so that's an array. Again, items that are the same type are stored together, so the position of each element can be calculated or retrieved easily by an index. And so the first item in the array is typically in the first position, second item in the second position, and so on and so forth. All right. And so the next data structure we'll be looking at is a linked list. And because an array has such a limitation of fixed length in memory, I think that's the motivation of having a linked list. A linked list is kind of like an array. It stores collection of items also in a linear order and has the same typical ordering an array has. So the first element is in the position 1. Well, if you're a computer scientist, that'll be 0. Second element is position 1. Third element is position 2. And that's how a linked list is ordered. So it's linearly ordered. And each element within a linked list is called a node. And in a linked list, it contains data items in one node, as well as a reference or link to the next item in the list. And so remember, we raised the indication on and with a link to the next computer's memory. And so with a linked list, what you find is that you typically do not have the restrictive nature of an array. You also do not have the restrictive size limitation that an array also has. And you almost get the same benefits that an array has. The only problem with the linked list is that for data access, it's not as fast as you would get with an array. So let's analyze this array, for example. The array has 4 indexes, which is 4, let's call it 4 slots in memory, right? And I want to get the 4th item, for example. If I know the address of the first element in memory and I want to get the 4th one, typically I would know the address of the first element in memory. All I need to do to get the first one, or the 4th one rather, would be to add 4 to the address of the first element in memory, and I can jump to the 4th location easily. Now with a linked list, on the other hand, what happens is if I want to get the 4th element within a linked list, I would first have to start from the first element and then get the link to the next element, go to the 2nd element, get the link to the 3rd element, jump to the 3rd element, then get the link to the 4th element before I eventually get to the 4th element. So I have to go through the whole thing from the top to get to any value or any element I need to get out from the linked list. Meanwhile, an array doesn't have that limitation. So it's the trade-off between using a linked list and an array. So you can imagine that this already informs you as to what kind of tasks or problems that you can solve. Imagine what problems or tasks can be better solved using an array list or a linked list. In a situation where you have to use or store elements where you do not already know the predefined length or size of the elements you need to store, it would be best to use a linked list or a list generally. But in a situation where you know what exactly you need to store and the exact size of what you need to store, you typically will want to use an array because it will be better suited for that task. Meanwhile, there's also certain types of lists that you can find in certain languages. For example, in Java, there's something called an array list. And an array list, like the name suggests, is a list that is backed by an array in memory. So you typically get the same performance you will get with an array using a linked list. But what happens in that case is that your runtime for your language, whatever language you use, in the case of Java, the runtime, which is the JVM, the Java virtual machine, what it does is that anytime it first instantiates or assigns a fixed length of memory to the array list. And then anytime you get to that limit or that length, what it then does is it destroys the first list, but before it does destroy it, it destroys the first array rather, but before it does destroy the array, it creates an array double the size of the first array, copies all of the content of the first array into the new array, and then destroys the first array. And so that's how the situation is with an array list under the hood. All right, so we will move on to the next one on the list. It's called a stack. How a stack works is that typically items are stored from top to bottom, but items can only be retrieved, or rather items are stored from bottom to top, but items can only be retrieved from the top, right? So if you look at the image below, it shows that the first item goes in and goes all the way to the bottom, or it's at the bottom. And then the last item is at the top. And so if we're ever to get anything out of this data structure, we always have to take out stuff or elements from the top before we can eventually get to the bottom. So the data structure is also called a last in, first out data structure. It stores collection of items in a linear order. Both the last item that goes in is the first item that comes out. And so a real world example I can use is typically when I was trying to avoid using the word stack, but I think eventually I have to use it. Typically when we stack items, for example, say a book, say you have a bookshelf, or say on your table, on your reading table, you have a stack of books on maybe beside your computer or something. And if you typically want to take out an item from that stack of books, you want to take out a book from the stack. I mean, because you're a human being, you're ideally not a computer, you could lift up, a couple of books, right? And then take out like a book from the middle of the stack. And so what you notice is that everything before that book that you took out, you have to take out. Say you have 6 books on your table, and you needed to take out the 4th book. The 4th book being number 4 book from the bottom book being number 1, the top book being number 6, and you needed to take out the 4th book from the stack. What you realize that you do is you take out the 2 books from the top, which is book 6 and book 5, before you then take out book 4. And so that's how a stack also works in any programming language. Before you access any element within the stack, you typically have to take out everything that's already on top, or the particular element you need to take out. And there are 2 operations that are are associated with a stack. One is called push, and the other is called pop. So when you pop an item, it means to take off, and then when you push an item, it means to put on the stack. All right. So you can keep the questions coming. If you have any question, or raise your hand to ask a question if you want. I mean, I don't want it to be just my voice you hear. So anyone who has a question or who thinks you have a contribution, you can raise your hand. I can unmute your mic and then have you speak. All right, next we look at a queue. A queue is a data structure that also stores items like a stack. Typically, everything is stored linearly. However, the operation order can only be first in, first out. Everyone in this room should be familiar with a queue. Everyone of us must have queued at one point or another in our lives. And so it's a very self-explanatory data structure. Whatever goes in first will come out first. And I can imagine how annoyed, many of us will feel when we're on a queue and someone has to cut us off. That's a very terrible feeling, right, for some of us. And so that's the representation of what a queue is in real life. The first person who gets there typically should be the first person who gets what they need to get, or gets attended to. It's not nice when someone else comes from nowhere and cuts into a queue and gets attended to. So that's the same representation in the programming language for a queue. And then a tree. Yeah, everyone knows a tree. I can imagine. A tree also stores data in a non-linear version. A tree stores data in a non-linear collection of items in an abstract way, and it is hierarchical. Each point on a tree is called a node. In this case, each node is associated with a key value, with the parent nodes linked to the child nodes or subnodes, as in anyone you want to call it, it's fine. And there's one root node that is the ancestor of all the nodes in the tree. Think of this as something like also your family tree. Typically, you have a father that everyone would referred to as the roots, or father and mother together as the roots, and then the children as the child nodes. So this image is an image of a binary search tree, which is a kind of tree, and it has something called the root, and then everything else is called a node. And then within a tree, you can also have something called a subtree, where there's a where a parent is also a child to another node. And then you also have things called leaf nodes, which are nodes that do not have any child nodes, similar to leaves on a tree. Okay. And then another interesting data structure that we can look at is a graph. A graph stores a collection of items in a non-linear fashion. I know some people will already say that a graph looks like a tree, but I'll make the distinction shortly. Graphs are made up of a finite set of nodes, also known as vertices, and lines that connect them, also known as edges. They are very useful for representing real-world systems such as computer networks. Now, the major difference between a graph and a node is that a graph doesn't have something called a parent or a root. Meanwhile, a tree has a root. And a graph is best, or a graph best represents relationships where there really isn't a single source. And so you need to show connections between multiple points or elements, really. And so you typically would represent such or structure such data using a graph. Meanwhile, if you needed to hierarchically represent something in memory or in any programming language, your go-to data structure would be a tree. Say, for example, you needed to represent a family tree. So you're creating an app that keeps records or family records, and you needed to store all that data. Typically, you want to store that using a tree. And then say, for example, you need to show relationship between friends. Say you have a group of 8 friends, and you needed to show relationships between who knew who. If you look at this image, for example, let's use the first element, which is 0, right? Assuming 0 is one friend within this network, we see that the 0th friend knows the first friend, the 0th friend only knows the first friend, and the 3rd friend, as well as the 4th friend. Which other connection can I make? So 0th friend knows the first friend, 0th friend knows the 3rd friend, the 0th friend knows the 4th friend. Now that's, so we can say 0 knows 3 people within this network. Now we can move on to the first friend and see how many friends the first one knows within the network. And we see that the first one knows the 0th one, also knows the second one, and knows the 3rd one, the 4th, and the 5th one. So that the friends at the position 1 knows more friends within the network than 0. So again, it's best used to represent relationships where we can have an infinite number of connections. Think of something like Facebook, for example. You see, sometimes you get suggestions, right? And the algorithm, I mean, which is something we'll look at later. The algorithm for that is I can already imagine is represented using something like a graph. The data that's used within the algorithm for friend suggestions on Facebook will be will be a graph that shows relationships between people. So if you know someone on Facebook and you know someone else also on Facebook, say you have 2 friends, those 2 friends will probably get suggested to each other as someone they know, because Facebook algorithm will predict that because there's a similar friend or there's a mutual friend between two people, they probably should know each other, or they probably would know each other in the real world. And so that prediction can happen based on such a relationship that can be structured in memory using a graph. All right. And then I think this should be the last one we look at. It's called a trie. It's a special kind of tree. It's a tree-based data structure. A trie is also known as a keyword tree, and it's a data structure that stores strings as data items that can be organized in a visual graph. A representative image is below. We see, for example, that starts out this tree. There's, for example, a letter T. So let's go down the path that has T on the left-hand side. When you move from the empty circle, you go to T, and then from T, you see that you have two connections to O and E. Now, if we go down the part of E from T, we then move on to TE as two letters. And then we see that we have three connections from TE to TEA, TED, and TEN. Now, notice that these three are words. First word being T, second word being third, and the third word being 10. And notice how they all have something called a weight. For example, 10 has a weight 12, 10 has a weight 4, and T has a weight 3. Now, many of us would have used spell checkers, or many of us would have used Google before and seen the word suggestion feature at work when doing Google searches. So for example, you go to, if you try and go to Google today, you can just try it as you speak, type in the first letter T. You typically will get a couple of suggestions for words that start with T. And this is how in the within the program that typically would happen. Google would first check the feature for word suggestion, would first check words that have a connection with the first letter being T. It probably would suggest to you a couple of words, and then say you type in another letter, TE. It then checks again which words have TE starting them. And so you typically see a list of words that you can then complete as the word that you originally were looking for. And so I'd imagine in that list, you'd have, say you typed in TE, you probably have words suggested to you such as 10, TED, and T in that order. Because 10 will probably have a higher order of occurrence, TED will probably have the next higher order of occurrence, and T will probably have the next after TED. So you probably see something like 10, TED, and T as suggestions when you type in the letters TE. And so it's based on this kind of data structure that things like word suggestions happen. Also, for example, many of us have used spell checkers in Microsoft Word, and then we see that when we type out a word, Microsoft Word can already tell us that that word is incorrect, if that word is incorrect or not. And sometimes we type in a word and it's correct, but then we don't, it still gets flagged as incorrect. And so in that case, many of us find that we have to add the word to the dictionary. Reason being that the word isn't already mapped within a trie. And so if your word processor looks for the mapping using a trie, for example, takes the first letter of the word, sees that there's no connection to the second letter within its trie data set, it will probably tell you that the word is incorrect. And so if you do add it to the dictionary, the algorithm is smart enough to start to make those connections within the trie. All right, so let me check the chat for any questions. Yeah, somebody's asking if a graph LinkedIn connection models. Yeah, probably, yeah. So I think LinkedIn connection models also. So or maybe not. I think for LinkedIn connection models, because LinkedIn has something that they use to tell you what level of friendship you have with someone. So you can be on a second level connection, rather not friendship. I mean connection level. So you can be on a second connection level with someone. Typically means the person is connected to someone connected to you. If you're on a third level connection with someone, it means the person is connected to someone who's connected to someone who's connected to you. And so in this LinkedIn situation, it probably would not be a graph. It probably would be a tree in that case, because with a tree you can tell the levels, just like a family tree, right? But on Facebook, it'll probably be a graph. I hope that answers your question, Maxwell. You can let me know if you have more questions. Okay, who else? Okay, someone says it's just hearing the try or keyword tree for the first time. Yeah, it happens, which is why you need to really, I mean, which is why we're having this session anyway. So to just really get you into all of this, and so you start to understand these things, and be able to build better software and write really good applications. All right, so I'll just do a quick recap. We looked at types of data structures. We looked at an array, we looked at a linked list. An array is a collection of items at adjoining memory locations. A linked list is also a collection of items in a linear order, but not at adjoining memory locations. And so what you have is a starting node called a head and a link to the next node. And so that's how a linked list is structured in memory. A stack, on the other hand, is a lasting first out data structure. It means what goes in last comes out first. And I represented that using a stack of books on your desk. And I said, assume you have 6 books and you needed to take out the 4th book. Typically, you take out first the 6th book and the 5th book from that stack of books before you're able to take out the 4th book. And that's how a stack looks like in the real world. And then also, yeah, somebody's asking if you can use a try for other things aside word suggestions. Well, I mean, you could, oh, that was Omotayo, you could come across a task or a problem that has a similar structure as word suggestion. I just also said you could use it for something like spell checker, right? So a spell checker typically would use a try, for example, right? And so you could also come across other things within a domain where you work, and you're trying to solve something, and you find that the problem is really similar to something that you would you would already use the try fan, so you can just go ahead and use that. Okay, somebody's talking about time complexity. We get to time complexity when we talk about algorithms. Somebody's also talking about how to Tajudeen also asked, how do we evaluate the big goal for linked-based graph tries? We'll get to all of this when we talk about algorithms. We'll look at how to evaluate each and every, maybe not everything, but then we'll talk about evaluating the complexities of the data structures as well as algorithms generally. All right. So after the stack, we talked about queues. A queue typically is a first in, first out data structure, which means that whatever is in the queue first comes out of the queue first. So there are two methods associated with the queue. The first one being DQ and the second one being NQ. All right. The next, we also saw a tree, and a tree is a hierarchical representation of abstract data. And as I think of it as something like a family tree. Now, everyone in the family isn't typically the same, but you can represent or structure or depict the structure of the family using something called a family tree, which just shows you how every family is composed, really. And so the most prominent thing about a tree is that it has something called a root, which is typically the starting point of the tree, and then has uh, things called child nodes or subnodes. And then the nodes that aren't connected to any other nodes are called leaf nodes. There are other things to know about trees, but I mean, these are the basics. And so, like I said, originally before we started, this isn't really a boot camp in the sense that boot camps are naturally short, intensive, and rigorous, but this is a boot camp in the sense that it boots you up to start to look more deeply into all of these things we're talking about today, right? All right, moving on, we also saw a graph, which is a collection of items in a non-linear fashion. Graphs are made up of a finite set of nodes and then connections that shows the relationships between each and every node. And nodes are also called vertices with graphs. And yeah, a useful representation really for a useful real-world representation for a graph is something such as computer networks. Like you can have a set of computers that are connected to each other, but each one really isn't necessarily connected to every other one within the network. And so you can use a graph to show connections between computers and which computers are connected to which. And then yes, we said a trie was a tree-based data structure that typically stores strings as data items that can be organized in a visual graph. Yes, somebody's asking, we need to know when to use one of each in the next course, the pros and the cons. There aren't really pros and cons per se of data structures. Really, they're just best situations to use which. There's a situation for every data structure. And so the advantages of a data structure really stand out when you have a situation where you can apply a data structure. And so maybe we can look at situations. I mean, the challenge for the bootcamp would give you problems that would allow you to demonstrate your understanding of when to use which data structure. And so even if you're not able to solve each challenge within or between now and tomorrow or by tomorrow, we'll also just look at each challenge and explain how each data structure is best suited for the situation. And yeah, so what to know basically, I think the most important thing to take out of this, Alan, is to understand each and every data structure. And when you do come across a problem, it would immediately pop out, in your head. It would immediately what's the word? It would immediately, just align in your memory to say, this problem looks like what I can use, for example, a linked list to solve. I mean, I made a distinction between an array and a linked list to say, if you have a situation where you needed to store something that you knew the exact size of, then it would be better to use an array. But if you didn't know beforehand the exact size of what you needed to store, you typically would want to use a linked list, because a linked list does not have the restriction of the size that an array has. And so if you have a well-rounded understanding or knowledge of each data structure, when you see a problem or task, it typically just jumps at you what data structure will be best suited for that, for the solution of that problem. And so there aren't really any pros and cons with any of the data structures. They're just best situations to use each. So I mean, if you do solve a problem that you needed a stack for using a queue, you might have performance issues like we've already seen from previous slides. And so that's where you really can then talk about pros and cons. Maybe when you see a problem and you start to compare which data structures to use, that's when you start to pick out the pros or the cons of using that data structure, particularly to the problem at hand. Yeah, so there are generally no pros and cons with data structures. All right, that's Q&A. Let me just also check the chat. Nothing, no questions in the chat that I can see yet. All right, so okay, there was one more data structure that we hadn't looked at. It's called a hash table, or also called a hash map. Now, many of us would have heard about a map, not necessarily a hash map or hash table. But yeah, they're pretty much the same thing. They're used interchangeably. So if you hear a hash table or a hash map, just know they're the same thing. And it stores a collection of items in an associative array that plots keys to values. I mean, that's a mouthful, but I'll explain it shortly. A hash table uses a hash function to convert an index to an array of buckets that contain the desired data item. So what it means when we say a hash map stores a collection of items in an associative array that plots keys to values, we're only saying that with every value that you store in a hash map, there's a key to retrieve it. So typically when you are putting something in a hash map, you store it using a key. And then when you need to get out any value from a hash map, you retrieve it using that key. So a hash map is a key to value mapping. It's a table that has on one column keys and on another column values. That's similar to any table that you're already familiar with. So I mean, the image below shows a table, first column index and the second column value. So if you were to get the value at for example, on this table, you have to get value 1 out of the hash map, you will use the index 0 to get it out. Now, when storing the value 1 into the hash map, how you typically will store it is put in the value and then use 0 as the key for that value. That's how that works. I'm not sure if we can see a practical demonstration of that, but maybe in tomorrow's session, we'll definitely be able to demonstrate some of that. And then Omotayo is asking, what's the difference between hash and object, please? Do you mean the hash ID? Omotayo, do you want to unmute and ask your question? When you say hash and object, what do you mean? So I can try to explain it or answer it as best as I can from my understanding of the question. The object is the value that's stored in the hash map. And then the key that is used to store that value is eventually hashed. And so the process of getting that key is called hashing using a hash function. So the hash or the result of hashing is what results or what is the key. And then the object is what's stored as the value. I mean, using the table image that you see below, the object is stored as the value. Meanwhile, the hash or the key is hashed, and then used to index or used to retrieve that object from memory later on when we do need it. Okay, Tajuddin, you said hash tables use key value pair, same as objects, both are data structure. I mean, maybe you're talking from JavaScript, but every object, I mean, if you're referring to, I mean, unless you're talking about, I'm not sure. Tajuddin, do you want to unmute and speak, or maybe I can also just try to answer this again. Hash tables use key value pair, same as objects, both are data structure. So an object, yeah, is an abstract data type, not necessarily a data structure. So an object represents something. You can have a collection of objects. So when we talk about data structures, we're typically talking about how to organize objects, how to store, retrieve, process, and organize objects, right? That's so when we say a data structure is used to store, retrieve, organize, and process a collection, typically we're saying it's a collection of objects. Now, every object has something called a hash ID and an equals method. When you store, or I mean, I'm not referring to a hash map in this case in terms of the data structure itself, but how your runtime, the runtime of your language, stores objects in memory is by using the object's hash ID. All right. I hope that's explanatory. Tajuddin. Alan said in Java, it's a hash map with key and value, same as dictionary in Python. Yeah, that's it. But an object has uh no, hash tables use key value pairs, same as object. So an object has something called the hash ID, but an object is not a key value pair data structure. An object is not a data structure. An object is an abstract data type which you can build an element out of to store in a data structure. All right. Unless you're also talking about JSON, which is JavaScript. A hash map is an object.
Yeah, I hope the session has been interesting for each and every one of us. And IG is going to continue giving us more and more concepts, but still feel free to ask any questions in the chat, and we'll do our best to answer each and every question. And then the links to all the platforms have also been shared with you in the chat. But if you did not receive them, feel free to ask them. And I think IG, you can take over.
Yeah, apologies, I dropped off. Network. Okay. I'll just reshare my screen and continue where I left off. I just hope everyone heard the explanation I gave about hash map, objects, abstract data type, and all. Okay, Daniel, please confirm you can see my screen.
Yes, I can see the screen, and I think Omotayo confirms that he had what you said about hash maps.
Okay, so yeah, Mata, you were saying hash table is you were saying So I mean, I was talking about the JSON representation, but that's not to be confused with what I explained earlier. So we can talk about JSON representation of all this later on. All right. So yeah, now that we've looked at all the data structures, that's not an exhaustive list anyway, I must say. I mean, just that's like the high level visualization of data structures. There's a whole lot more. I mean, for example, with trees, there are other tree-based data structures. There are binary trees. You could look at a data structure and see different implementations or sub-implementations of each data structure. There's like I said, for example, for tree-based data structures, there's binary tree, there's a balanced tree. There's just a couple for lists. For example, there's linked list, there's array list, there's what else? There's also a couple of other list-based data structures. And then for linked list, array list, there's cyclic linked list. That's a twist to a linked list. For which one can I mention again? Yeah, I was also going to say for maps, yes. There's hash maps. There are other types of maps also. And so I think there's a tree map, if I remember correctly. That's in Java. Yeah, Omota, are asking if a set is a data structure. Yes, a set is a data structure that does not allow duplicates. Apologies, people. Sharing my slides shortly. All right, I think I'm in presentation mode now. Please, everyone confirm, anyone confirm I'm in presentation mode? Awesome. Yeah, so I was saying, yeah, Tajidin is a set is a data structure that doesn't allow duplicates. So it's similar to an array, but just imagine an array without duplicates. All right. So it's also a special kind of data structure. All right. So on the high level, yeah, Oluwaseyi just gave a better explanation. So a set is a collection of objects, but doesn't allow duplicates. All right, so characteristics of data structures based on all the ones we're saying, and which is not, like I said, not exhaustive, it's just a representative list. I mean, but it gives you a good start to explore more into other areas of or other types of data structures and just look at them holistically. I mean, and then also look at them specifically and using the lenses of whatever programming language that you use, because they all have different implementations in different languages. Yeah, okay, Ramon. Okay, let me just recap a hash map for Ramon, or maybe we'll come back. Okay, I think we have some time, so let me recap. Ramon says he didn't hear me when I was talking about a hash map. So yeah, a hash map, also called a hash table, stores a collection of items in an associative array that plots keys to values. What that means is that a hash map is like a table. For example, imagine that you create a table in Microsoft Word with two columns. And on the first column, you call that index or key column, and the next column you call it the value column, right? And whatever you put in the key column is what you can use to retrieve the value in the value column. That's typically how a hash map is, or what a hash map is. It's a data structure that allows you to store values using something called a hash ID, and that has the hash map also has something called a hash function that converts your key into a hash ID. And then when you put in that key into an operation that you use to get out data from a hash map, it gives you the corresponding value, the value that corresponds to the key. So it's simply a table that has keys on one column and values on another column, and you can use the values of the keys you can use the keys to retrieve the values on the columns for values. I hope I did not so confuse you, and I hope I tried to explain it. So it's a key plus value pair data structure. And yeah, that's what it is. So our data is stored using keys, and data is retrieved from it using keys. And something that interesting that I need to mention is you can store, typically when you store a value using a key in this data structure, and then you try to store another value using that same key, what happens is it overrides the first value. I mean, that's what you'd imagine would happen, right? But in practice, that's what happens. Then secondly, you can have two objects that have the same hash ID but are not equal. Remember, a hash ID is the result of passing through a key through the hash function of a hash table. So in practice, or in theory, you can have two keys that have the same hash ID, but they are not going to correspond to the same object. But in this case, I'm not referring to a hash table within your programming language. I'm referring to a hash table like within your runtime, but it can still be applied to a hash table within your programming language, because you can use objects as keys, and you can have two objects that have the same hash ID and not have the same and not be equal to each other, and not have the same the equals method saying they are the same. So in that case, what happens is that the hash map creates a bucket. Now, if you look at the second line of the definition, a hash table uses a hash function to convert an index into an array of buckets that contains the desired data, in this case, items. So if you have two objects that have the same hash ID and use them as keys within a hash map, what happens is that your map creates one value of that key, or rather your map creates one key based on the hash function. But then if you save two items that have like I said, two different objects that have the same hash ID as a key with two different values, you will then have within the value column, instead of having one item, you'll have two items. And so what happens is that when you come back to retrieve an item, you have a bucket that you can retrieve from, and the hash map converts that object that you used as a key originally using the hash function, gets the hash, and then also then uses the equals method to get the exact object that you're looking for in the map. I will demo this. Please, someone remind me later. I will demo this. So it can be confusing to talk about, maybe because I'm not structuring my thoughts. But we can demo this later, and then maybe someone can just bring it up if it's interesting to anyone, and then I can demo this to you and show you how two objects can have the same hash, but then not be the same. And so they can be the same key within a hash map, but they will store different values within the hash map. Yeah, so Chibuzo, interestingly, I was just explaining how to handle how a hash map handles key collisions when the hash function generates the same index for the key. I didn't even see your question before I started explaining it. So I can demo this tomorrow, or yeah, not today. Yeah, but I mean, Chibuzo, do you already get an idea of how a hash map resolves key collisions? Okay, awesome. Okay, so I can move on to the next slide now. Okay, so based on the data structures we already saw, we can draw the foreign, or we can use these characteristics that we're about to look at to then talk about the data structures and be able to organize them using this or these same characteristics. So we have seen linear and non-linear data structures. It describes whether items, data items are arranged sequentially, such as with an array, or in an unordered sequence, such as with a graph. So you can either say a data structure is a linear or non-linear data structure. You can also say whether a data structure is homogeneous or heterogeneous based on whether the items within the given array, within the given data structure are of the same type. One example is a collection of elements in an array or various types, such as abstract data types defined as a structure in C or a class specification in Java. Typically, for an array, you would store a collection of elements that are of the same type. And so you can say an array is homogeneous. Meanwhile, a hash map typically is not homogeneous because you can have keys. Let me backtrack a bit. You can have a homogeneous hash map, yeah? You can have a homogeneous map, right? That's correct. You can have or we can say, we can also have a heterogeneous hash map, right? But with arrays, typically we would have arrays that are naturally homogeneous. But let me make a clear distinction so it's not confusing, or so that I don't confuse anyone. So if we're using the what do we call what's this called now? If we're using I can't remember the term, and then if I explain it, you might not properly understand it. Why did I forget this now? All right, these things happen. So if you are using the data types that are I just can't remember the term, so I'm going to skip it anyway. But I mean, I hope we get a sense of homogeneous and heterogeneous. Max was asking, heterogeneous keys inside of a hash can by string, number, or other data types. So with heterogeneous or with hash maps, you can use homogeneous keys as well as heterogeneous keys, which is why I said the hash map can be any. Really, it depends on how you eventually store the data within the data structure. So, but for certain data structures, I mean, like an array, when you define the array, you already determine what objects you want to store within the array. And so you're typically going to store only the same types of objects within that array. Yeah. For hash maps, you can specify what type of key to use, but it can be an abstract data type. And so it's not necessarily any of the usual suspects like strings or numbers. It can be an object, yeah, and because it's an abstract data type, in that case, it really can be heterogeneous. All right. All right, then we can also say whether a data structure is static or dynamic. This characteristic describes how the data structure is compiled. Static data structures will typically have fixed sizes, structures, and memory locations at compile time, while dynamic data structures would have sizes, structures, and memory locations that can either shrink or expand depending on the use. So I'm going to ask a question, and I just want everyone to respond in the chat. What data structure comes to mind when you think about a static data structure, for example? Awesome. An array, yes. And then the second one is more like it. So what data structure would be dynamic? Looks like an array, but it's not an array. Yeah, a list, a linked list, so that would be dynamic. Array list, linked list, typically lists. Awesome. All right, so a quick look at how we can hierarchically represent data structures. So types of data structures. Yes, the term I was looking for before was primitive data types. So we typically have primitive data types of types of integer, floats, character, boolean. I think every language in the world, every programming language in the world should have one of each. Every language should have an integer, floating point, numbers, characters, and booleans, right? And then, so types of data structures, the primitive data structures, typically the data types really are integers, floats, characters, booleans. The non-primitive data structures are either linear or non-linear data structures. Under linear data structures, we have arrays, we have stacks, we have queues, and we have linked lists. Under non-linear data structures, we have trees, we have graphs, we have tries, and we have a hash table. All right. And I hope this is very self-explanatory. Otherwise, if you have any questions, you could also just go ahead and ask. If you're not sure why a data structure is under the section that it is under, please just drop a question or drop something in the chat, and then I can explain. All right, so I'm about to move on from this screen. All right, so somebody did ask the pros and cons of each data structure. So, and I answered that really data structures do not have pros and cons. Rather, they have considerations when picking them. So there are certain things you should consider before you pick out a data structure. Firstly, you have to decide what kind of information you want to store. And based on that, you can then pick a data structure. Secondly, how will the information be used? Do you want, or are you tackling a task where when you put in information, you want to get out the last information that was put in, then you want to use a stack? Or do you want to get the information that was first put in? You might want to use a queue. Okay, so maybe I'll use a real world example for this. Now, most of us use browsers, Chrome, Edge, Safari, what's this other one? Firefox, right? And then we typically browse sometimes, and then we go to a back page. Sometimes we go back in history, right? We just keep hitting the back button. Up until we get to like a page in the like an earlier page that we want to reference. And then when we do get to the earlier page, we can also just click on the next button and go to the page where we came back from, right? And so maybe I'll ask this first and see if anyone can answer it. I think so. Of course, definitely people will be able to answer it in the room. But maybe I should just explain it so in case anyone who can't answer it can have an idea of how to solve it, right? Remember, I earlier said that lists typically have different implementations. I mentioned array list. A linked list itself is an implementation for a list. All right. Oluwaseyi has said it's a linked list. But in this case, somebody also said linked list. Well, in this case, it won't exactly be a linked list. It will be something called a cyclic linked list. The difference between a linked list and a cyclic linked list is that a list has in a node information to go from its current position to the next element in memory. But a cyclic linked list, within the node, it has information to go to the next element in the list, as well as information to go to the previous element within the list itself. So a linked list is one directional, really. You start from the head and you go all the way to the bottom. But with a cyclic linked list, you can jump from a position to either the previous element within the list or the next element within the list. So you can represent such a behavior of using the back and forward button within a browser using a cyclic linked list. All right, so just again, I mean, I'll provide resources that you can look at. Yeah, or a doubly linked list. Who said that? John was asking what's a doubly linked list then. I mean, I hope I'm not confusing both terms. So let me just check that. Oh, apologies. Yeah, doubly linked list. Yeah, John, thanks for your question. So it's a doubly linked list. I mean, I already wasn't mentioning it or mentioning cyclic. Cyclic linked list is another implementation of a linked list, and so that has a different behavior. But yeah, actually, everyone in the room, I apologize. I was describing a doubly linked list. I'm calling it a cyclic linked list. Yeah. Thanks, John. Yeah. Cyclic linked list has a different behavior. So the first element has a link to the last element, and the last element has a link to the first element. So that's what a cyclic linked list is. That's just confusing both terms in my head. All right. So the third consideration for picking out a data structure is where should the data persist, or where do you keep the data after it is created? So this is a big consideration when you are picking out your data structure, and so that then informs you on when you consider how you're going to store your data. Then you also want to know what the choice of database to use would be. And so when you're picking out your data structure, considering what algorithm you want to create and the problem you want to solve, you're also thinking about how you're going to persist the data, and that will also influence what data structure you do pick. All right, Alan, I think this slide is dedicated to you. Yeah, Chibuzo, I did say we'll consider the cost of retrieval when we talk about algorithm performances in the algorithm section of this whole bootcamp. So when we talk about algorithm performance, we'll talk about cost of retrieval for some of these data structures. All right. Then the fourth consideration will be, again, what is the best way to organize the data? And so if when you decide what the best way to organize the data, you want to process comes to you, when you have that information or when you have thought about it, you can then know what data structure best suits your problem. And then also you want to consider what aspects of memory and storage reservation management you want to consider. So, when you use an array, you use a continuous space in memory. And when you use a linked list, you use a non-linear space in memory. And so if you do when you do consider that, or when you have that consideration, you can also, that can also inform you on what data structure to use. Yeah. All right, Alan, I hope this does help in terms of answering how to know when to use each data structure, not necessarily pros and cons. Uh, okay. All right. I was hoping for some reaction from Alan, but maybe we can move on and Alan can. Alan, if you have any more questions, please drop them in the chat, yeah? All right, so again, having looked at the factors to consider when picking a data structure, we'll now also look at how to choose a data structure. When choosing a data structure for program or application, what other things, what should the developer consider? You have to first answer the three questions, or these three questions. What operations or what functions does your program need? Based on that, you can pick data structures that are aligned with the operations that your program wants to support. Also, computational complexity. What level of computational performance is tolerable? For speed, a data structure whose operations execute in time linear to the number of items managed using big O notation will be faster than a data structure whose operation executes in time proportional to the square of the number of items managed, that is big O of n squared. And so Chibuzo would expand more on computational complexity in terms of retrieval from data structures, hopefully tomorrow. All right, then also programming elegance. Yeah. Programming elegance are the organization of data structures and its functional interface easy to use. If you're looking at how easy it will be to use the data structure, I mean, from the operations, you can already have an idea of how easy it is to use a data structure for the particular problem that you're trying to solve, and then that would also inform which data structure to pick in that case. All right, so real world examples, just some of it, not an exhaustive list again. Linked lists are best used if a program is managing a collection of items that don't need to be ordered, and items that for adding them to the collection, it requires only constant time. So big of one is required for adding items to linked list, or for removing items from the collection. Also that takes that should take big of n, and then an increased search time is okay. So searching through a list typically would require more time, and so if you don't mind increased search time, and then you definitely want something that you can use uh, by I mean adding elements to it in constant time, as well as not requiring the need to have an ordered collection. A linked list is typically the best thing for you. Yeah. And then stacks are best used if the program is managing a collection that needs to support a last in, first out order. I think this is self-explanatory. Queues should be used if the program is managing a collection that needs to support a first in, first out order, also self-explanatory, right? Again, some real world examples. Binary trees are good for managing a collection of items with a parent-child relationship, such as a family tree. A binary search tree, which is also a tree, is appropriate for managing a sorted collection where the goal is to optimize the time it takes to find specific items in the collection. A graph works best if the application will analyze connectivity and relationships amongst a collection of individuals, such as in a social network like Facebook, for example. All right, most of this content was pulled from this source. I would also provide certain resources to give you a deep dive into more stuff about data structures generally, and then just to really get you into the meat and heart of everything we've talked about today. Now I will take questions. If you have any, please use the Q&A or raise up your hand or drop me a chat and I'll try to answer. Probably just give maybe 5 minutes. Or otherwise, I'll just wait 1 minute to see if any questions come in. Okay, Maxwell wanted to go back to the last slide for binary tree and binary search tree. This one? Questions, people. Someone says there's a hand. I don't see the hand, Blaine.
Yes, there's a hand from Ayodeji. Ayodeji, you can unmute and then ask your question.
All right, before I did, I think I'm not sure if it's unmuting. Oluwaseyi, you're asking how you can learn to become a software engineer developer. And this is where it starts from, really. Understanding or starting to understand data structures and algorithms is a great way to start to learn to become a software engineer, as well as checking out our learning platform. Daniel already put the link in the chat, so you can scroll up, or Daniel, if you'll be gracious enough to just put the link again in the chat. And then there's a course that I'd highly recommend. Just going to get a link and put it in the chat for anyone who wants to get a start in software engineering, or generally just want to improve their coding skills. A course that I would highly recommend, and it's for free. You don't have to pay anything. I'll drop the link in the chat. It's called Introduction to Computer Science and Programming, CS50. That's the title of the course. Just give me a second to get the link. Okay, so I just put it in the chat. Check. No, I sent it as a DM. So I'm putting it in the chat now. It's Introduction to Computer Science, CS50 on EDX. You can take the course for free. It's an amazing course. It will make you or put you on the path to become an absolutely amazing software engineer. If you do sign up for the course and have questions or need some guidance, although there's already a lot of support that's provided by the course staff, but if you do have questions, I think what I'll do is leave my mail in the chat, and then you can email me for those who are not already on the Tonga platform. Otherwise, you can email me here, and then if you have any further questions on the course, or just to give you general guidance on or into software engineering. Yeah. All right. I see or hear someone else has a hand up. So Oluwaseyi, I dropped the link for you if you're still there. Check it out. So Ayodeji is not. I don't think Ayodeji is here. All right. So I'll move on.
Yes, thank you so much, IG, for taking us through today's session. And this is just the first of many. We are also going to have more sessions running tomorrow up until Friday for particularly looking at data structures and algorithms. And we'll look forward to having all of you back to complete this interesting bootcamp. And there are a lot of resources, learning materials, all available in the Tonga platforms and products that I shared earlier. And the links are available in the chat. You can just check it out. And I hope this was a very fruitful session for each and every one of us.
Yeah, that's it. I wanted to also drop the link for practice. There's a link to certain tasks you can practice using some of the data structures that we already talked about today. Follow the link, sign up. There are four tasks that you can practice with. There's a task for using an array. There's a task for using a linked list. There's a task for using a queue, as well as a task for using a stack. And so check those out. Get your hands dirty. Use your preferred language. See what you come up with. See if you have questions. That's what we'll tackle tomorrow. We'll do some live coding problem solutions, and then just answer our general questions. Yeah. All right, and then I was also going to ask Maxwell. You asked for me to backtrack to a slide. Did you have a question from that slide? Okay, Maxwell said he did not. All right, Daniel, please take it away.
Yeah, thank you so much once again, Oghomwen, and to everyone that was able to make it for this particular session from the beginning until the end. Like the wise man once said, every good thing comes to an end, and this brings us to the end of today's session. However, this is not the end of the bootcamp. We're still running till Friday, same time, same place. So feel free to come again, and you can also invite your friends and colleagues who you think might need these computer science concepts because they're very vital for writing very good code, and also to help you to think about problems once you find them out in the real world. And so IG has shared a link where you can do practice for these data structures we've shared today. So please check it out and try to attempt it, and then we can always review them tomorrow. Other than that, thank you so much for your participation, and we hope to see you again tomorrow.